My guest today is Professor Emil Martinec, who's Professor of Physics at the Enrico Fermi Institute and the College of the University of Chicago. His research focuses on string theory and particle physics. Welcome, Emil.
Hi.
So this is a subject that I know very little about, and that makes it very exciting for me. So we're going to have maybe 2 or 3 conversations around this. It's a deep subject. I think the general public have heard string theory, fascinated about it, but maybe don't know a lot about it. So I want to sort of rewind time a little bit and establish the idea why string theory might be needed. So the way that I understand this, Emil, is that late 1600s, Isaac Newton proposed the law of universal gravitation. It was deterministic. It had predictable power in many of the things that we were measuring at that time, but it couldn't quite explain how it worked. It was sort of Einstein called in a different context spooky action at a distance. This was also spooky action at a distance in 1700s. And then late 1800, James Clerk Maxwell came up with sort of the first unification of magnetism and electricity. And then we had quite a few advancements right after that. And so could you talk a bit about the other 2? So we had gravity and electromagnetism established early on. And then we figured there are 2 other fundamental forces, right? So we have 4 of them now. So what is the progression there?
Yeah. So it's probably best to start with Newton. I mean, if we're going to take sort of a big picture of where did modern theoretical physics come from? I think really you can trace the history back to Newton. And the idea that if you want to formulate, the motion of bodies as some set of mathematical equations, first of all, the mathematics didn't exist for Newton. So the first thing he had to do was invent the calculus. Okay, and that's kind of a theme in theoretical physics that advances in our understanding of how to quantify the laws of nature come hand in hand with advances in the mathematics in which to express those laws of nature. And so indeed, Newton invented the calculus, and then he invented his, maybe every person with a little bit of science education learns about Newton's 3 laws of motion, right? And the one that's important for dynamics is the idea that force equals mass times acceleration, and so acceleration is the way that bodies begin to move. And so what Newton's law tells you is that if there's some force acting on the body, it starts to change its state of motion. And so the way the calculus comes in is to say that and the way sort of deterministic dynamics played out for subsequent centuries is the idea that if you hand me the positions and velocities of all of the particles around you at some instant of time, then specify for me what are the forces acting on all of those particles. Then Newton says, okay, the force determines how the particles' velocities are changing, and I can gradually, evolve those equations forward in time to determine the subsequent evolution forever after. So there's this idea of a sort of a deterministic dynamics. You lay down some initial condition. There's some laws of motion that determine the subsequent evolution of that data forward in time. And then, so the state of the universe, forever after is determined. And in a way, one of his first applications of those laws of motion was to gravitation. And I don't know if you want to call this the first bit of unification of physics, but the idea that the gravity as we experience it on Earth, as force governing, how apples fall from trees, is the same force that governs the motion of the planets as they orbit the sun. That's sort of, two different, very different contexts in which there are two seemingly different forces of nature are really all different aspects of the same thing, maybe on different scales, but are really the same underlying phenomenon.
Yeah, so that's an interesting way to think about it. So it is sort of as you say, it's a first unification. We see practical applications of a phenomenon, but we think they are different things.
Yeah.
So he brought it to a common framework and
That's
wrote down an equation. That is sort of the first unification, right?
Yeah. So it's sort of like, the dropping of an apple, it's falling some distance of, a few meters, is a vastly different scale than the distance between the Earth and the Sun, which is, millions of kilometers. So, the fact that the same force can act on vastly different scales and produce seemingly different phenomena is something that we strive to do in formulating laws of nature. You say there are only 4 fundamental forces. Well, we see an immense variety of phenomena in the world. The idea that one can somehow reduce the laws of physics to such a small number of seemingly fundamental forces is, in a way, a great triumph of the last several hundred years of progress in theoretical physics.
Yeah. So and then Maxwell shows up with with another big brain, so to speak, and does something really remarkable, and that is unifying electricity and magnetism, right?
Yeah. So there is a situation where, in the beginnings of the 19th century, people were discovering electricity and magnetism, and realizing that, for instance, if you put a compass needle next to a wire that's carrying electricity, that the compass needle doesn't point north anymore. It shifts its orientation in response to the nearby electric forces in the wire. And so that was the sort of an indication that there might be some relation between electricity and magnetism. And there were, a number of 19th century physicists, Faraday, Ampere, I mean, I could list a whole bunch of names, that started formulating laws of electricity, laws of magnetism, and ways in which they were related. And so the grand synthesis came with Maxwell in the 1850s to say that I can write down for you a small number of mathematical equations, again, in the spirit of Newton. And these mathematical equations govern all phenomena involving electricity and magnetism. And there was a prediction that came out of those formulas that he wrote down, and in a way began a big sea change in the way we conceptualize physics. So, prior to Maxwell, one of the laws of electricity was Coulomb's determination of what's the force between two charged particles. But it actually looks very much like the force between two masses, which was measured by British physicist Cavendish, of what was called the inverse square law. That is, if I have two masses, then the force between them under gravity is proportional to each of their masses, and falling off like 1 over the distance squared between them. Okay, and Coulomb's law of electromagnetism looks very similar. You just replace the masses by the electric charges. So 2 electric charges interact with a force which is inversely proportional to the square of the distance between them, and also proportional to how much charge each one has.
Yeah.
And with Maxwell, the sort of and the ideas that led up to Maxwell was the idea that it's not that there's this, as you called it spooky action at a distance, that somehow this particle instantaneously generates a force on this particle. The idea that sprung up is that the particle, the first particle, say, has associated to it what's called an electric field. That is, permeating space around it is a field that responds to the electric charge. And so what happens is that locally in space, the electric field is disturbed by this particle, and that disturbance propagates through space by a set of equations, and those are Maxwell's equations, telling you how the electric field and the magnetic field propagate from point to point in space. And so charges and the motion of charges, motion of charges are electric currents. And so charges and the corresponding electric currents of moving charges create electric and magnetic fields. Those fields move in space from one place to another. And then the particle over here says, oh, I'm in a non-trivial electric and magnetic field, and I'm a charged particle, so I should respond to the electric and magnetic field in my vicinity. And so it changes this spooky action at a distance to a very sort of logical propagation of influences from one place to another through the medium of a field, in this case, the electromagnetic field. And
yeah, so I want to touch back on Newton very quickly. So this guy should have had a lot of time on his hands. In addition to inventing calculus, he set humanity on a path of arrogance in some way, that you can write down equations that determine how things work, and humanity has never been the same after that, right?
Yeah, well, it confers a lot of power in that these equations have very practical consequences for the world around us, and how we can influence the world around, not just see things in the world around us, but also influence the world around us. I mean, everything in our modern age is well, not everything, but so many things in our modern age, the electronic age, are consequences of these equations that were written down, 170 years ago. And so, for instance, one of the very first consequences of Maxwell's equations was that, he was thinking about describing phenomena like, currents running through wires and, magnets and things like that. And what he discovered was that, in order for the electric field and magnetic field created by this charge over here to influence this field, this charged particle over here, as I was saying, the influence has to propagate. Well, how fast does it propagate? It propagates with the speed of light. And so an immediate consequence of Maxwell's equations was that light is an electromagnetic phenomenon. That there is a prediction that if you move around electric charges, that you create electromagnetic waves, and those waves travel with the speed of light. And that prediction was took 30 years, but Heinrich Hertz, the German physicist, used moving electric charges in a wire to make radio waves, and that's why we, denominate the frequency of electromagnetic waves as having hertz as their units. And so the equations, sometimes have unforeseen consequences, which then lead to predictions, which lead to experimental verifications, and then yesterday's experimental verification becomes tomorrow's laboratory tool. And so much of what we do is to manipulate electric and magnetic fields to our benefit.
Yeah, so we'll come back to this, Emil. So as you say, equations are useful. Sometimes we may have equations that we don't understand yet, but if you have equations, that could be quite useful to think about things. So we can think about that in the string theory context later. And I want to sort of skip over general theory of relativity and quantum mechanics. And so these other two forces, the strong force and the weak force, when did we find them?
So the strong and weak nuclear forces, I would say the sort of beginnings of our understanding of them come with the discovery of radioactivity in the turn of the 20th century. Finding this, well, so maybe the first thing we should say is that throughout much of the 19th century, we didn't even understand that there were atoms. The idea that matter comes in discrete quanta, that there are these underlying particles, electrons and protons and so on, that make up matter, didn't really come until around that time, when people were able to isolate the particles and detect some of their properties. And so the electron was discovered in the late 1890s as something that was emitted by vacuum tubes, forerunners of transistors.
That is J.J. Thomson?
J.J. Thomson, yes.
Yeah.
And then there was the discovery of natural. So he just discovered what were then called beta rays. I mean, the terminology is long since disused, but that he discovered this sort of like particle being emitted by this vacuum tube, and that it was bent by electric and magnetic fields, and you determine its mass and charge and so on. So there was also naturally occurring radioactivity in certain materials. That, for instance, Marie Curie was one of the leading physicists discovering various forms of radioactivity.
With 2 Nobel Prizes, I will add.
2 Nobel, yes. And so wasn't fully understood what was creating these particles of radioactivity. And now we understand it as the fact that atoms have nuclei made out of protons and neutrons. And sometimes those configurations of protons and neutrons aren't entirely stable. And they may decay over some period of time. And different materials have different amounts of natural radioactivity depending on how unstable their nuclei are. So there.
Let me ask you this, Emil. So on the strong force side, it is sort of counterintuitive from without knowing much about it. I mean, you can't have protons of same positive charge sort of staying together, right? Was that the issue?
So the strong force. So there are 2 things to say. So let me put the radioactivity aside for the moment and talk about atomic nuclei. So you're quite right. One of the laws of electricity and magnetism is that if 2 particles have the same kind of charge, the same sign of electric charge, then the force they experience is repulsive. They tend to try to push each other apart. Whereas if the 2 charges have the opposite sign, like say an electron and a proton, they attract. Yeah. So the idea that an electron and a proton, say in a hydrogen atom, can make a bound state seems perfectly natural because the electron and the proton are attracted to one another. And so if they get close enough, the force that keeps them, revolving around each other is reasonably strong, and the hydrogen atom is stable. Okay. But if I look at helium, which has two protons, well, the protons have the same, all protons are the same. And in particular, they have the same electric charge. So why don't the two protons in the helium nucleus, repel one another and fly apart? And the answer is the strong nuclear force. That there's not only the electromagnetic force that's causing the protons to repel, but also there's an additional force, the strong nuclear force, which electrons don't feel, but protons do, and neutrons do as well. And so the nucleus is bound together by these strong nuclear forces that keep the protons from being unstable.
So if I don't know if I understand this, Emil. So will it be correct in thinking that this is very strong, but it's in very short space? Yes. Because the nucleus is pretty small, right?
Yes. So the idea is the stability of nuclei. So if you ask, what stabilizes nuclei? Well, we don't see any helium atoms with just two protons and no neutrons. It seems like they always come with at least one and often two neutrons, and that it's only the combination of the two protons and the two neutrons together that are sufficient to sort of bind everything together in a stable way. And if you look at the periodic table, that's sort of a theme, that the the sort of number of protons and the number of neutrons is approximately equal for most nuclei. And the reason is that there's this electrostatic repulsion that the protons are feeling. So the way you can beat the electrostatic, the electric force that's repelling the protons, is to add more strong force. And the way you add more strong force is if you add neutrons to the nucleus, then you've added more nuclear attraction, because both the neutrons and the protons feel the strong nuclear force. But you've sort of diluted the electrostatic repulsion, because that's only felt by the protons. So the neutrons bring in sort of more strong force attraction without at the same time bringing in more electrostatic repulsion. And so that's sort of the thing that stabilizes the nuclei.
Oh, wow. Okay. Yeah, I had no clue about this. So you have to have certain number of neutrons in the nucleus for it to be stable.
Yeah. And so you see this all over the periodic table. So the idea that there's sort of a sort of normal range of stability of nuclear matter, at least as we see it in the atomic nucleus, is this balance. And I should say that what I'm describing is sort of the theory of nuclear forces as it existed, say, in the 1930s, when people thought that the fundamental particles were the proton and the neutron, and certain particles that carried the strong nuclear force between them, like we were talking before about the electromagnetic field sort of binding things together. The thinking was that there was some kind of force, strong force. In this case, the thinking was that it was mediated by a particle called the pion, which by that time had been discovered in nuclear collisions. And so, again, it was sort of the same idea that there are fundamental particles, that there are forces, and the way the forces propagate between the different matter constituents is by the exchange of, in the case of electromagnetism, it's by exchanging photons, the particle of light. In the case of the strong nuclear force, it's by exchanging pions. It was thought at that time that the pion was sort of the force carrier.
But we moved on.
But we
We
moved
moved
on,
on from that, right?
and
So what is our current understanding there? Is it
so
gluons or something like that?
yes. So we now understand that actually there's yet another layer of structure that both this pion, the force carrier, and the protons and neutrons are themselves composites of more fundamental particles, namely the quarks and gluons of the strong.
It's the Russian doll game.
Yes, very much so. But you know, part of the hubris of string theory, which we'll get to in the end, is you know, the notion that there's a last layer to the Russian doll. You know, that you can't.
But there's a limit to it. I mean, we will get to it. We cannot go anything beyond 10 to the minus 35 meters or something like that, right? It's a Planck length. So,
that's right. That there are fundamental limits to how small you can make things. But right now we're talking about sort of the you know, scales of the size of the atomic nucleus. And so, as you say, the nuclear force has a finite range. In the original, you know, conception of the 1930s, it was because the pion sort of had a finite range of propagation, and so that sort of limited the range over which the strong nuclear force would be experienced by strongly interacting particles. Now we understand it as something else. It's that the strong force is truly strong, and if you try to take a quark and rip it out of a proton, it says, I don't like that, and immediately creates a stream of strongly interacting so-called gluons, or the theory of the current theory of the strong interactions is now modeled very much on on Maxwell's model, Maxwell's idea that the fundamental charged particles are the quarks, and that the force carriers, instead of being photons, they're these particles called gluons. And we even use the same, and because there are sort of three kinds of charge in the strong interactions, people gave the name color to describe it. And physicists are always sort of playing with language in describing things and trying to use our experience of you know, language and describing things to sort of borrow the same concepts to describe much more alien things happening in the subatomic realm. And so so the idea is that the quarks carry this color charge, and that there are three kinds of colors. So people call them, you know, red, green, and blue, in analogy to the sort of three basic colors of nature. Right. And so, like, and the idea is that anything which is colored emits the strong force by emitting a field of gluons around it. And the problem is that if you try to pull something away and get an isolated colored particle, in the same way you get an isolated charged particle in electromagnetism, the problem is that it costs you more and more energy. The reason it's called the strong force is that the amount of energy it costs you increases with the distance that you try to pull it away, rather than
sort of the other way around, right? So
it's the other way around.
Gravity, distance,
gravity and electromagnetism die off with distance. Colored particles feel a force which increases with the distance. And this was actually kind of part of the origin of string theory, that what our you know, modern understanding is that what's happening is that the chromoelectric, let's call them chromoelectric and chromomagnetic fields, which is actually the terminology that people use. The charge is called color, and so the sort of field that's emitted by a colored object are chromoelectric and chromomagnetic fields. And what happens is that the chromoelectric and chromomagnetic fields are confined to a narrow tubular region between the separating particles. And so that sort of little sort of rubber band, if you like, or that region of excited chromoelectric and chromomagnetic field, is something which, if I try to separate the particles, it costs me the energy to create more and more chromoelectric and chromomagnetic field. And roughly speaking, the energy it costs me is proportional to the distance I separate them, not dying off like the separation.
Is the practical intuition I have, Emil, I don't know if this is the right thing. So could I think about this as sort of connected by a spring?
Yes.
The further you sort of move them around, the more force they have to come together, something like that.
That's right. So it's the same idea as a rubber band, right? If I have a rubber band, if I want to stretch the rubber band, I have to apply a force, and the amount of energy I have to supply to stretch the rubber band a certain distance is proportional to the distance. And so, if you like, the amount of work I have to do in order to stretch the rubber band, and the more I want to stretch it, the more I have to work. Okay.
So they're physically connected, but they're magnetically and electrically connected. It works almost the same way, so to speak.
That's right. And eventually, if you pull them apart far enough, you create, we've skipped over Einstein, but one of Einstein's famous formulas.
Who cares about Einstein? What did he do?
Well, one of his famous formulas is E equals mc squared. Okay. So eventually, and remember we're talking about, subatomic distances, and the energies that are involved are nuclear energies. And so eventually, if I try to pull these colored particles far enough apart, the amount of energy I have to supply in order to do that is equal to the energy that is needed to make two new particles.
Oh, wow. Yeah, that's a lot.
So that's a lot of energy. So what I can do is to say, okay, I can take some of the energy in these chromoelectric and chromomagnetic fields and use it to create a particle-antiparticle pair, a new pair of quarks. And one quark goes off with the one I'm pulling this way, and the other quark goes off with the one I'm going this way. And now, if the color charges cancel, I've created something which has no net color charge, and they can go off and separate their merry way as color neutral objects. And so
takes a tremendous amount of energy. So that is not, from a strong force perspective, generally not possible. So what's the weak force? How does that work, and what does that do?
Right. So So let me just finish off the strong forces, and then we'll move on to the weak force. So the idea is that everything we see in nature, I like the isolated atomic nuclei, protons, neutrons, all these particles are themselves net color neutral. And the reason, and this is where, as I was saying, the physicists like to borrow terminology to sort of guide their thinking. The proton has 3 quarks inside it, and each one carries its own color charge, red, green, and blue. But we know we learn in color theory that if you combine equal amounts of red, green, and blue, you make white light, which has no color. And so it works the same way, roughly speaking, in the theory of the strong forces, that if I have a red quark, a green quark, and a blue quark, as an aggregate, they carry no net color charge. And so the proton can be, pulled away from other protons and neutrons without having, to supply a force proportional to the distance, because the proton itself is a color neutral object. And what was thought of in the 1930s as this, pions, carrying the strong force between protons and neutrons, is some kind of residue of this more microscopic phenomenon that 2 protons can exchange a pion, the pion is itself a quark and an antiquark, again, color neutral. And so, so that you sort of at somewhat larger distances than the size of a proton, we have this sort of residual part of the strong force, which consists of the sort of color neutral parts of the strong force playing with each other through residual interactions of further strongly interacting particles. And so but you know, those do have consequences.
Yeah.
So for instance, when people started turning on particle accelerators in the 1950s and 60s, they started seeing more and more strongly interacting particles. And
so when was Fermi on?
Fermi's initial work as a physicist dates back to the late 20s, early 30s. He died in the middle 1950s.
No, I meant the Fermi accelerator. When was it?
Fermi accelerator. So that turned on in the late 1950s, early 1960s. And the similar particle accelerator turned on at CERN in Geneva, Switzerland. But at the time of the 1950s, the sort of scale of energy that was required to do these, you know, nuclear scattering experiments wasn't that huge. You know, it didn't take you a device which was like miles in circumference. You could fit it inside a reasonable university laboratory building. And so, roughly speaking, every major university had their own particle accelerator with some energy which was of order billion electron volts, which is sort of the scale of the mass of a proton. As I was saying, you know, you need energies which are of order, you know, the mass of a proton in order to create these strongly interacting particles. But people sort of kept on, you know, making bigger and more fancy accelerators with more and more energy, and they kept on seeing more and more strongly interacting particles, you know, as decay products of their collisions. And so the question became, what's the organizing principle, you know, governing these particles? And they started observing certain, you know, regular patterns in the spectrum of the particles and their masses and their spins and other properties. And that's one of the sort of first evidences for this sort of what I would call a phenomenological string. This chromoelectric flux tube, which is the way we now understand it, you know, fundamentally, was just really this sort of like electric, this you know, rubber band, if you like, which is binding the particles together. And that if you know, slam two pieces of it together, you know, you might start it spinning like crazy, and its, you know, centrifugal force is enough to stretch it. And so, you know, that leads to a prediction that, you know, if I give something a lot of spin, the centrifugal force stretches it, but the stretching costs me energy, and energy is mass. So I observe a relation between the spin and the mass. And this is indeed what was observed in accelerators and was the first evidence for something like a string theory. And that's where sort of string theory entered particle physics. It's not where its eventual home was. Its eventual home was not just the strong interactions, but almost everything. But the idea that there could be some utility for describing some part of nature using, you know, fundamental objects which were strings rather than particles dates to that time.
So is it the same thing as sort of thinking about linear? Is the thing about momentum and mass or something along those lines, and be finding a relationship between the two? So things sort of spinning around.
It was a relation between mass and spin. So what people would do is they would plot they would say, okay, let's make a two-dimensional plot. Okay, one axis we'll say is the mass, the other axis is the spin. Okay, and so let's take all the data, you know, the different particles that we see coming out of our accelerator, and let's, you know, plot our measurements of their mass and spin. and they just started seeing them lying on, uniformly spaced. Well, there's uniformly spaced because spin in quantum mechanics is quantized, so it comes in discrete units
Right.
of Planck's constant. A half, 1, 2, 3 halves, 2, etc. And so people were seeing, regular recurrences of every time you looked for a particle of higher spin, it would come at a higher mass. And then, once you plot a number of these particles, you start drawing straight lines through the plots and searching for what's a dynamical reason for such a regularity in the pattern of masses and spins.
Yeah, there's always a good story behind a regression straight line. So I guess I would imagine.
Yeah, of course, the question is, are you seeing something fundamental, or are you just seeing some kind of a pattern? The pattern should have an explanation. One of the issues in theoretical physics is trying to decide what patterns in data are indicative of something deep, and what are just consequences of something else. And so it turned out that in this case, this sort of string-like behavior was not something fundamental. It was sort of a byproduct of this property that chromoelectric flux likes to confine itself to narrow tubes in subatomic strongly interacting particles.
So now let's touch on the weak force.
Yes.
So what exactly is it? How do we measure it? How do we know it exists?
Okay. Well, this isn't necessarily the way it was first discovered, but maybe the cleanest explanation is that, when people were first finding what they thought were the fundamental subatomic particles in the 1930s, we had the electron since Thomson. We have the proton because we know about hydrogen atoms as being a bound state of an electron and a proton. And so, the atomic nucleus then, the periodic table, started teaching us there had to be something besides protons in the atomic nucleus, and that's the neutron. And so, around 1930-ish, Chadwick, the physicist, discovered the neutron in particle accelerators. I should say, a neutral particle is very difficult to detect, right? Because most of our detectors function electromagnetically, right? So you have, some, you see the charged particle over here, and some other charged particle whizzes by. This one gets deflected, and so you measure the charged particles in your apparatus. Okay, but if you have some charged particle in your apparatus and a neutron goes by, the neutron has no electromagnetic field. And if it's far enough away from this charged particle that it doesn't see the finite range of the nuclear forces, it's as if it whizzed by and the detector didn't respond.
Yeah.
So, in a sense, it's only when the neutron hits something like another nucleus that you sort of detect its presence. Okay. Still, people were able to produce neutrons and sort of slow them down. Because usually you have some subatomic particle accelerator, you whiz two nuclei into each other, and it creates some spray of particles coming out. Okay, but those spray of particles is traveling at close to the speed of light, and so that very quickly leaves your detector, and you sort of lose your track of it. So what you want to do is sort of find some way of sort of slowing down the decay products so that you can sort of capture them and measure their properties. And so people started figuring out, what's a way of slowing down these byproducts of these nuclear collisions. And eventually were able to sort of slow down neutrons enough that they could sort of capture them and study their properties. And one of the things they determined was that the neutron all by itself, outside of atomic nuclei, is unstable. It wants to decay into an electron and a proton.
Oh, wow. Okay.
And so people started measuring that process, And the first thing they saw was that this process of the neutron decaying into an electron and a proton didn't seem to conserve energy. And, and conservation laws in physics are, sacrosanct.
I like the Bible.
Yeah. So, I mean, they're called laws for a reason. and so the proposal was made, if I'm remembering correctly, by Pauli, that a way to save our cherished conservation law of energy was to postulate there's another particle called the neutrino, and which we now understand is another fundamental particle. But it's even more elusive than the neutron, because not only does it carry no electric charge, it also doesn't respond to the strong force.
It doesn't have much mass either, right? I mean, it's very minute.
Doesn't have much mass either. And so it's just sort of a, almost ghost-like. There are I don't know how many powers of 10, billions of neutrinos, roughly. I don't know, millions, billions, any of that ilk, neutrinos streaming through you and me at the moment, right? Because the radioactive processes in the sun generate neutrinos. So part of the radiation from the sun is not just light, but neutrinos. And so there are neutrinos streaming through our body coming from the sun all the time. But, we're not particularly perturbed. They don't, knock us around in any way. They just keep on happily streaming right through us. And the reason they keep streaming right through us is that their rate of interaction with all the other particles that we're made of is extremely tiny. And so that's the weak force, that the way that a neutron decays is, again, by another one of these force carriers. In this case, they're called the weak bosons, sometimes called W and Z bosons. And they are the carriers of the weak force. And so what happens is that, remember I said the neutron and the proton were made up of 3 quarks. In the case of the proton, it's so that the quarks are given fanciful names up and down for the things that make up protons and neutrons. And the proton is 2 ups and a down, whereas the neutron is 2 downs and an up. And the way that the weak nuclear force works is that in the process of emitting a W or a Z boson, in the process of emitting a W boson, an up quark turns into a down quark. So it's a very peculiar kind of a force. It's a force which changes the nature of the particles themselves.
Yeah, it sort of changes a Democrat to a Republican, so to speak.
Yeah, very much so. So in the process of emitting a W boson, a neutron turns into a proton. The W boson itself is unstable, so it wants to decay into some other weakly interacting particles. And the available energy, you'd have to find, so if you've already, the neutron is slightly heavier than the proton. So the mass difference between the proton and the neutron is a certain amount of mass difference, which is an energy difference according to Einstein, E equals mc squared. So that creates for you an amount of available energy. And so if the W boson is to decay, it has to decay into 2 particles whose total mass is lighter than the mass difference of the neutron and the proton. So you look around for, and you also have to conserve charge. So you turn the neutron, which carries no electric charge, into a proton. So to balance the electric charge, you need something with the opposite charge of the proton, and the only thing around is the electron.
Right.
And so the W boson has to decay into an electron and this other particle, this neutrino. And so what happens is a neutron decays into a proton, an electron, and a neutrino, and that's the weak, and that's sort of the quintessential weak interaction, is that process.
So the weak interaction sort of drives radioactivity. Is that the right way to think about it?
Right. So suppose we have carbon-14. Okay, this thing we use to date fossils. Okay, that's a carbon atom. Carbon atoms are actually, I think I may be getting this wrong. Carbon-14 may actually be the wrong thing to
Decay.
Yeah, that may actually be a strong decay. No.
Doesn't matter. I mean,
Doesn't matter.
Yeah.
But conceptually, there are atomic nuclei that aren't quite stable. And they're not stable because they have too many neutrons. And so the way they decay is if you know, suppose, just for the sake of argument, suppose it's like, you know, suppose I was right about carbon-14. So carbon-14 is something that has, to be carbon, it has to have 6 protons in it. That's the atomic number, charge of a carbon nucleus. So then it has 8 neutrons. Okay, the stable version that's in most, you know, materials around us is carbon-12, which is 6 neutrons and 6 protons. Okay, so to turn carbon-14 into carbon-12, well, for carbon-14 to decay, that you want one of the neutrons to decay into a proton. Doesn't turn into carbon because you have one more proton. Okay, so now you're looking for an atomic nucleus which has, instead of 8 protons, 6 protons and 8 neutrons, you're looking for one that has 7 of each.
Okay.
So you can do that if you say turn one of the neutrons into a proton, and you know, the excess energy escapes as electrons and neutrinos. Okay, so that's the process by which carbon-14 decays. It doesn't become carbon-12; it becomes nitrogen-14. Right. So nitrogen is the atomic nucleus which has atomic charge 7, and has 7 neutrons and 7 protons. So I think I actually got it right. So there are nuclear decay processes whereby the atomic nucleus decays through this weak interaction, spitting out electrons and neutrinos, and leaving behind a nucleus which has more of a balance between the number of neutrons and protons.
Is this a predictable process, Emil? I mean, could we sort of, given time and quantity, could we say what would happen?
Statistically, yes. Okay, so you know, so this is a process that's governed by quantum mechanics, and so it's not predictive in the sense that if I told you the initial position and velocity of all of the particles in the atomic nucleus, I could predict, you know, when and how and where the nucleus decays. So we haven't talked about quantum mechanics yet, but quantum mechanics is predictive, but in a probabilistic way, in the sense that it predicts the probabilities of things happening, not the certainties of things happening. And so given enough carbon-14 nuclei, what you can predict is what fraction of them will decay, you know, per hour, say, or per year. Right. Okay, and that's how we date things. It's like we look, you know, that carbon-14 is created in the atmosphere through cosmic ray collisions, and so anything that's living breathes in carbon-14. Once it dies, it stops breathing, so it's no longer taking in carbon-14. So all the carbon-14 atoms start decaying into nitrogen. And so if you look and what's the proportion of the carbon-12 versus the carbon-14, you get an idea of how old something is.
Because so that's the carbon dating process.
That's how carbon dating works. It's basically relies on this weak nuclear force.
So we have these 4 fundamental forces: gravity, electromagnetism, strong force, and weak force. And the standard model appears to be extremely successful, combining three of them.
Yes.
But not the fourth one, right? So we probably have to come back tomorrow to talk more about it. But I just want you to set the context for it. So there is a level of discomfort in physics. There are two extremely successful theories. Einstein's theory of general relativity, it seems to explain things in large distances and a big scale. And quantum mechanics is exceptionally successful in explaining everything else, so to speak.
It's very in the subatomic realm. It's
yeah. So, but physics is about, sort of having a very elegant combined framework. We cannot have two gods. There has to be a singular God, and we haven't found her yet. So that is really where we're heading, right?
Yeah. That's right.
So to set the context for why we are seeking string theory.
Right. So, we began on this journey of reductionism, trying to find underlying causes for the phenomena that we observe in nature, which is not to say, sometimes my condensed matter colleagues chafe at the use of the word fundamental in what particle physics, so as if what they're doing is somehow not equally important. And so there is a whole other thing that one should talk about is that, once you have the sort of fundamental description of nature, explaining from the standard model, how the climate works, okay, is, building back through all of these layers that you peeled away to find the standard model, okay? And then each layer is itself a whole set of complicated equations that you have to go solve. So let's be clear on what the aims are. It's not like we're trying to, explain every phenomenon in nature by the use of for fundamental forces. It's more, sort of a proof of principle that underlying everything are these fundamental forces, and that the idea being that with a big enough computer and those laws of nature, that you could in principle work your way back up and explain more complicated things in terms of these elementary forces, and so that sort of spirit of trying to find ever more deep layers of the nature has been the driving force, from Newton through Maxwell into quantum mechanics and the 1930s and 1940s, when we were first understanding the strong and weak forces, on through to the post-war era, where we were finally getting enough energy that the standard model kind of came into view, and with a final flourish in the 1960s and early 1970s, where we understood that each of these forces, the strong force, the weak force, the electromagnetic force, are all have the same Maxwell-like description. That is, there are particles that are charged under these forces. They emit the analogs of electric and magnetic fields. They're just, chromomagnetic or weak magnetic and electric forces, and those are the ways by which particles interact. And in the particle physics realm, that's it. I mean, this theory has been confirmed in exquisite precision. Some of the experiments to like 10 decimal places. I mean, just extraordinary precision for an experimentalist to achieve. And so, by now there's absolutely no question that at the scales that we've tested, this is the theory. Okay, but okay, we never sit on our laurels. We're always wanting more. And there's still one other force of nature that hasn't sort of been brought into the fold, and that indeed is the force of gravity. And part of the reason is that the gravitational force is extraordinarily weak. If you think about it, you're sitting in your chair, I'm sitting in my chair, because of the force of gravity of all of the rest of the Earth on you and me. Okay, so
I can just stand up,
and you can stand up, and so you can counteract the force of the entire Earth's gravity by standing up. Okay, so the amount of gravitational field that any individual atom in the Earth is exerting on you is extraordinarily tiny, compared to the electromagnetic forces, right, that act between charged objects. Those act over, those, a magnet, right? Magnet, sticks to a piece of iron with a pretty strong force if it's a strong magnet. Okay, so that's just a few atoms, and yet it's I can lift something up with a magnet, so the magnetic force is obviously exceeding the gravitational force. Yet the number of atoms in the magnet is much smaller than the number of atoms in the Earth. Okay, so that gives you an idea of how much smaller the gravitational force is than the other forces. And
so this is sorry, Emil. So this is a puzzle, right? So we look at the other three, and we can measure them. We can see them as really strong, measurable things. And then we have this fourth thing that appears extremely weak, and it perplexes us. And so I guess one question I have as with knowing nothing about it is that could it be that gravity is not a fundamental force? It is something different.
So people have tried that sort of approach. That gravity is somehow induced out of something else. Other things that people have thought about, the other theories are all quantum mechanical theories. You could worry, is gravity somehow not quantum mechanical and doesn't, follow the laws of quantum mechanics, but is just its own, pure Einsteinian, thing off by itself. And all of those sorts of ideas have their own conceptual difficulties and inconsistencies. And so our best understanding is that gravity should be brought into the fold, like with the other forces, and unified in some way. And so I should first say that Einstein's reformulation of Newton's theory of gravity is along the Maxwellian model, namely that you don't have two masses interacting at a distance. There's a gravitational field, and this body emits a gravitational field which propagates through space and time over to here, and then this body responds. And we know that to be the case because we've now detected gravitational waves.
Yeah.
So the analog of Hertz's experiment detecting radio waves has now been carried out, where we see two colliding black holes. It takes objects the size of, the sun colliding to emit enough gravitational energy that we can detect it as the faintest, radiation a billion light years away. And so it's the same model. It's that there's a gravitational field. It's emitted by every object in the universe because every object has either mass or energy, and mass and energy are equivalent. And since mass gravitates, energy gravitates. So even the photon gravitates. Even the photon has no mass; it has energy, and so it gravitates like everything else gravitates.
So I don't know much about this idea. So couldn't we take Maxwell's equation and reformulate it for gravity? I mean, it seems like it's sort of in the same neighborhood.
Yeah. So you might say, inverse force law proportional to the charges. Replace the charge by the mass. Kind of looks the same. So why don't we just write the same equations and erase a factor of 2 over here and so the reason is one of the reasons is that this idea that that the charge, the analog of the charge for gravity is energy.
Yeah.
And so that has a number of consequences. So I mean, so one thing is that it makes Einstein's theory very nonlinear in a way that electromagnetism isn't, because everything has energy. Even the graviton itself, if these gravitational waves that we're detecting with LIGO, right? We're detecting the energy that the wave is depositing in the detector. And so Einstein's theory is fundamentally different from Maxwell's theory because everything gravitates, even gravity gravitates. And so it's not going to be quite the same as Maxwell's theory. It's a little bit more akin to the strong interactions, because in the strong interactions, not only do the quarks carry color charges, the gluons that are transmitting the force themselves carry color charge. And that's actually part of what's responsible for the strong interactions having this property of increasing energy, is that the chromoelectric field that's spanning the distance between the quarks itself has some energy associated with the electric field interacting with itself. And so there are differences, but it's a field, what's called a field theory. You're describing the gravitational field and its dynamics. There's another aspect of it which is also kind of confusing conceptually, which is that in Maxwell's theory, we sort of lay out space and time as a background, sort of an arena in which dynamics takes place. Right? We say, okay, what did Newton say? Newton said, give me all of the constituents and their positions and velocities at some initial time, where tell me where they are, what their velocities are at some instant of time, and then I'll predict what happens in the future. Okay. Yeah. So space and time are sort of the arena in which all of that unfolds. And then along comes Einstein and says, no, first of all, the space and time are actually malleable concepts. That the sort of underlying structure of his theory is that the gravitational field is the geometry of space and time. And what's happening when I have a massive particle here, the gravitational field that it's emitting is a warping of, or curvature of, the geometry of space and time. And so that's part of the nonlinearity of the theory. In order to decide how things propagate from here to here and influence one another, you have to know what the geometry of space and time is to say what's the arena in which that propagation takes place. But that arena is itself the dynamical object. It's very self-referential.
Yeah, it's making my head spin, Emil. So we'll come back tomorrow and talk about sort of the history of. So let me finish up with this. So the issue that we have is that we haven't been able to combine the four forces into a singular theory. They seem to have emanated from different angles, and they seem to explain things at different scales.
Yes.
But that is not satisfying enough from a physics perspective.
Right.
So that's what you call the sort of the grand unification theory attempts, right?
Yeah. So I think tomorrow, if I could sort of lay out a plan, we should probably go back and cover in some detail the 20th part of the 20th century that we skipped, namely.
There's nothing that happened there, Emil. Come on.
Oh, come on.
You know, general theory of relativity, quantum mechanics. I mean, these
So
are.
we should touch on relativity and quantum mechanics, and in particular Einstein's theory of well, we already described a little bit Einstein's theory of gravity. Okay, but you know, just to sort of whet people's appetite to why it's a problem to combine Einstein's theory with all the other forces, is again this business that mass is energy, and energy and therefore energy governs the strength of gravitational interactions. So if we're looking for you know, as opposed to Maxwell's theory where you just fix the charges, okay, and you know that governs how strong the electric interactions, magnetic interactions are. In gravity, if you repeat the same experiment but you just collide the particles at higher energy, the gravitational forces are stronger because the strength of gravity is mass equals energy, and if the energy of the collision was bigger, then the force is stronger. And so you kind of running into a problem of peeling away this structure of nature and trying to find things that are ever more microscopic and higher energy, then you're going to run into a problem because gravity is going to become very strong. And the idea of unification is that around the natural scale of gravity, called the Planck scale, is very close to the energy at which it looks like all of the other three forces have also about the same strength of interaction. And so, you know, it's not guaranteed, but it's certainly suggestive that these forces have a common origin that stems from physics near what's called the Planck energy scale.
Right.
And so that's one of several reasons why one thinks that there should be some common structure underlying all of the forces, including gravity. But maybe that's.
You talk about this. Sorry to interrupt. Yeah.
No, I just say, but that's for the next installment.
Yeah, so we'll talk about this tomorrow. You know, I somehow feel like if everything's hidden in the Planck scale, in space and time, and it is not really approachable from an experimental perspective,
yes,
then God does have a sense of humor. Yeah, I mean, we can make all the theories we want, but we won't be able to really probe it at that scale, right? Is that true?
So we would have to be lucky, right? Because that scale is so remote. It's 16 orders of magnitude more energetic than our most powerful particle accelerators, you know, the LHC at CERN, for example.
Right.
So the likelihood that we would ever, in a laboratory setting, reach the scale of energies needed to confirm the theory, you know, at that energy, it's extremely unlikely. So we have to look for other sort of vestigial manifestations of interactions at that scale. And one place is cosmology, where there, you know, we think there was a Big Bang. And so there might have been, you know, energetic collisions on that scale going on in the early universe. And we could ask, you know, have the imprints of those violent early collisions sort of imprinted themselves somehow on the structure of cosmology that we see today? So that's one place. Another place is in black holes, where Einstein's theory breaks down. In the core of a black hole, there's supposedly, according to Einstein's theory, the core of a black hole has a singularity.
Yeah.
And what the singularity means is, once again, that collisions become arbitrarily energetic at the singularity. And so if Einstein's theory held all the way down to the singularity of a black hole, then you would need something to replace Einstein's theory to make sense of what happens there. Now, the unfortunate thing there, again, God is laughing at us once again, because surrounding the singularity of a black hole is an event horizon that says if you want to sit outside the black hole, then you can't see what's happening at the singularity. So you know what's going on, but you don't know much about it because you can't.
Yeah, it's like the US Congress. You can
right.
sit outside, but you don't know what the heck is going on inside.
That's
there.
right. You don't want to watch the sausage being made. So, to see the sausage being made, you'd have to dive into the black hole, but then you would become part of the sausage. so, not a recipe for a long-lived.
I think you physicists have so much fun. You guys have to pay the taxpayers rather than the other way around. I mean, a lot of people pay for the type of fun you guys are having.
I feel very fortunate in my career that I've been able to do what I love and earn a living at it. So yes, I feel blessed in that way. Yes.
No, it's a beautiful thing. So we'll come back tomorrow, and then we will talk about the forgotten theories of general theory of relativity and quantum mechanics.
Yes.
And then we'll go into string theory.
Yes, we can talk about Einstein and Schrodinger and Heisenberg and all of those other people we skipped over.
Yes. Excellent. Thanks so much,
All right.
Emil. Okay, talk to you tomorrow.
All right, take care.